I'm going to go fairly quickly through the remaining material in this thing. It does relate to things we've talked about already, namely the in-home geriatric assessment case study. But I do want to get back to the main line because I want to start talking about one of the main concepts that we'll be speaking about next week, namely this Bayesian cross-validation approach that I call calibration cross-validation, which in my view provides the most promising way to deal with model uncertainty in a well-calibrated fashion without having to use tremendous doses of really complicated software like Bayesian nonparametrics has to do, and really slow software like Bayesian nonparametrics has to do, and also software where you're not sure what you're getting in some senses from Bayesian model averaging and so on. So remember the in-home geriatric assessment study. We have people randomized into treatment and control, and we looked at a parametric model. Initially, we wrote down a parametric model that had fixed effects Poisson regression going on. But then we also moved from that to what we called a random effects Poisson regression model. And we could call it a parametric one, otherwise known as a PrEP model here, parametric random effects Poisson, PREP, because our model basically said everybody has their own theta, which is related to their propensity to become hospitalized. And basically, you can think of the thetas as related to the lambdas I talked about before, in that e to the theta corresponds to the lambda that we had before. And so log lambda corresponds to these thetas. So everybody has their own log lambda propensity of becoming hospitalized, and those are like independent draws from different Poissons where everybody has their own propensity to become hospitalized. And then the log lambdas, we would then say they're IID from some distribution G. And I showed you that the parametric random effects Poisson regression model we had took the random effects distribution to be known somehow as identically normal with mean mu and variance sigma squared. So this is a way to rewrite the what I called REPR model in that earlier work, random effects Poisson regression model. But we're putting all of our eggs into the Gaussian basket for the random effects when there isn't even any very good way to test whether that's true or not based upon the data. So what if that assumption's wrong? It would be great to try to remove that assumption by building a prior model on that capital G that we can center on the normal distribution, but it allows us to learn what the right answer is from the data rather than just dogmatically sticking with the normal. And so the formulation of that corresponds to this new idea. The first line of the model is the same. The second line of the model is the same. But now we let G be a draw from a Dirichlet process with parameters alpha and some centering distribution G0. And we let G0 stand for the standard normal distribution, which itself will have a little parameter vector, which is listed here with the symbol psi. I guess that's phi rather than psi, excuse me. And so this is a Bayesian nonparametric model 1. It's a kind of Poisson-Dirichlet process mixture model. And I won't go into details very much. It shows how you could actually, there are details that show how to do the Gibbs sampling in this model. Then there's a little section I'm not going to cover. You sometimes know for sure that a treatment always has an effect that goes in one direction. And I would argue, I have already argued to you guys earlier, that applies in this case here. Because of the way in-home geriatric assessment works, I find it hard to imagine that it could make things worse as far as people's health goes. So in my view, scientifically, we're trying to choose between a theory in which it just leaves things alone as far as outcomes are concerned versus another theory in which it makes things better. And so that corresponds to a stochastic ordering of the random effects distributions, and my colleague Thanasis Kotis worked out how to work with that. I'm not going to talk about that. And what we did to see how good these models were is we used the log scores idea. We created posterior predictive distributions for future data, and that's easy to do. There's details that I won't bore you with. And now I'm going to get to a slide that I would like to rotate. Does anybody remember how to rotate in PDF world in Acrobat? Is it something about, there's a view button, except unfortunately the view stuff Yeah, we're too far inside tools. Oh, I know another way to do it though. Let's see. Does Control R do a rotate? Doesn't seem to work. Control Shift R. Let's try that. No, that doesn't work either. Control Shift minus? Yes. Ah, thank you, sir. Give that man $1. Um, so what we did was we simulated a whole bunch of random effects distributions and a whole bunch of data sets that had different true stories for what was going on. So over there on the right, I'm showing you the CDFs for treatment and control. And in the first row of the story, the treatment and control CDFs are separated from each other in a simple fashion. They correspond to ordinary Gaussian CDFs, just where the treatment is doing a better job than the control is. The second one down represents, and the third one also, represents a situation where we have a mixture of two distributions for the random effects in one condition or the other one. And you can see that over in these histograms as well. The histogram for the control theta.c random effects in experiment 2 had a long right-hand tail for the control, and it had a bimodal story for the underlying random effects. And in experiment 3, we have the bimodality happening again, and of a slightly different nature. So we created several simulation environments where we knew what the right answer was. And also the third one had the property that things were both bimodal, and we had a stochastic ordering of the two treatments, which is something I'm not going to focus on. So I guess Control Shift plus would get me back. Hey. Okay, great. And so here are the predictive distributions using the parametric model and the Bayesian non-parametric model. The blue circles represent the prior, and the red circles represent the posterior. And so if we fit the parametric model to a data set that's bimodal, of course, the parametric model can't find that because it doesn't know anything about bimodality. And so it's going to do its best to compromise between the two modes, and it'll get that smooth curve like that. Whereas the Bayesian non-parametric model, which is not informed, by the way, about the bimodality in the prior, it's just given a single Gaussian in the prior with about 250 observations in each group, you may recall. It has no trouble picking up the bimodality. And so this is an example of Bayesian non-parametrics behaving adaptively and finding what the right structure is without being told what the right structure is. So that's pretty good. And we have some stuff here that's details. And now what I'm showing is some curves. Basically, these are normal random effects. This was data set 1. And what we have is posterior MCMC estimates of the random effects distributions for the parametric model in the first row and for the Bayesian non-parametric model in the second row. The right answer is the blue curves, if I remember correctly. The data generating answer is the blue curves. I'm trying to remember which. No, I think that's wrong. I think the blue dotted lines represent uncertainty bands according to the model, and then I'm not sure why the right answer isn't smooth. Maybe it actually is smooth and it just looks funny from the plotting. Okay, so let's take the black dotted lines as the truth, and the blue stuff as the estimates with uncertainty bands around them, 95% pointwise uncertainty bands. So you want to look for two things. You want to look for validity. Did the parametric model get the right answer? You want to ask, did the uncertainty bands always include the true black line? And the answer turns out to be pretty much yes in control and pretty much yes in treatment. Did the Bayesian non-parametric story get valid answers? Same question, same answer. But what's the principal difference between them? The Bayesian non-parametric uncertainty bands are wider. And that makes sense. In the space of all models, we're placing a more diffuse prior. We're saying we don't know what the sampling distribution is. And so no wonder you get wider uncertainty bands when you're using a more diffuse prior. That's a basic fact of what we've been doing the last 7 or 8 weeks, right? Less prior information, more posterior uncertainty, right? So there it is in this picture. So a person looking only at this slide would say, Well, I'm going to go with the parametric models. I like narrow uncertainty bands. And look, the parametric model gives narrow uncertainty bands. What are you basing on parametric guys doing? You get wide uncertainty bands, and they're needlessly wide. However, but it's cheating because we built the same parametric model. We used the same parametric model to fit the data as was the known data generating mechanism. So that's not right. But now let's start putting in skewed and bimodal random effects. And so the parametric answers are again in the top row, and the Bayesian non-parametric answers are in the bottom row. The right answer is the dotted black lines, and the blue lines are again the number that comes out of the actual procedure used with blue dotted lines for 95% uncertainty bands. Are the Bayesian non-parametric uncertainty bands still wider than the parametric bands? Yes. But what went wrong for the parametric story? That's right. Its bands are so narrow that it didn't catch what was really going on in the data. And so this is just like that thing I said to you guys either earlier today or at the end last time. You got a choice. You either give people narrow uncertainty bands that are narrower than they should be and therefore wrong more often than they should be, or you give people wider uncertainty bands that turn out to be right in a calibration sense. And so, yes, the Bayesian non-parametric uncertainty bands are wider, but they turn out to be wider by just the right amount so that they can adapt properly to what's actually going on in the data, which is, again, a nice, cool feature. And the stochastic order thing, I guess what we were going on here is to show that the top one is the Bayesian non-parametric model without stochastic ordering, and the bottom one is the Bayesian non-parametric modeling with stochastic ordering. And you can see over there on the left, when there actually is stochastic ordering, you get narrow uncertainty bands by putting in the stochastic ordering assumption. But that's just a kind of a second order thing that we're seeing here. So we created plots that showed the log scores and full sample log scores for the different models, and across different experiments and different treatment and control groups and so on. And basically what you want is higher, bigger than lower, higher, better than lower in all these pictures, where all the red things represent the Bayesian non-parametric models and all the non-red things are the parametric models. And what you see everywhere you look is either the models are tied or when they're different from each other, the Bayesian non-parametric model has bigger log scores, doing a better job of predictive validation. And so basically what's happening is that we have a way now, and it's not that hard, to fit random effects models without making restrictive and potentially incorrect parametric distributional assumptions about the random effects. We can learn the underlying random effects distributions from the data. So that finishes this particular handout. I'd like to return now for the remaining time to our big handout, part 5. So next time on page 36 of this handout, I'll show you a method that turns out to be an example of something I've been working on lately called distribution-free, well-calibrated Bayesian inference. I know in some specific examples of ways to produce well-calibrated Bayesian results that don't make any distributional assumptions at all, other than ones that are directly motivated by the exchangeability of the problem. And I'll show you some examples of that next time. There are some special cases. This is part of the story I was trying to tell you before of the form. It is possible to do what I called optimal Bayesian model specification without putting in any assumptions that are not actually organized based upon the design of the study. Does it look to you guys as though Bayesian non-parametrics achieves that goal? In effect, what we're doing now is we're expressing uncertainty about the sampling distribution through the Bayesian non-parametric prior. So is that like not actually assuming any particular sampling distribution that in your modeling that might turn out to be wrong? From what I've shown you today, is this an approach that looks like it comes close to achieving the goal of not assuming things you don't know? Well, in some of the examples I showed you today, the answer was yes. For example, in those curves I just showed you, the Bayesian non-parametric method with about 250 or 280 observations in each group successfully recovered structure when it wasn't told that structure was there. So that's an example of a method that actually, in that example, also does come close to my goal of not assuming things that you don't know to be true. You are centering the Bayesian nonparametric prior at some place, some centering distribution. But if you put a small value of C in the whole thing, then you're giving the Bayesian nonparametric story a chance to learn what the right answer is. And yet, the Bayesian nonparametric uncertainty bands tend to be quite wide. And so maybe what we're doing is we're creating a method that comes close to that goal of optimal model specification, except in the sense of not necessarily following the calibration principle. The effort to be fully not saying anything about the distribution might lead us to intervals that are wider than they're actually necessary by some other means that could also give us a similar goal with better calibration. And I'll show you some examples of that next time. I think this method, calibration cross-validation, that I've been working on lately, has potential to do even better than Bayesian nonparametric methods in producing well-calibrated answers that don't assume things you don't know. So, well, if you don't care about calibration, then you would be working with a utility function that was based only on things like how narrow your intervals are. And if you drove that to its extreme, you'd tell people there isn't any uncertainty at all and try to win a big prize based on how narrow your intervals are. Well, I'll give you intervals that all have width 0. Thank you very much. Can I have the prize? But as I showed you guys last time, when you write down a utility function that includes a reward for being well calibrated balanced against a penalty for how wide your intervals are, you find yourself making wider intervals just to make sure you get the bonus. And that's a cool thing. In the example I showed you last time with weather forecasting, the weather forecaster found it useful to make intervals that were actually corresponding to about 97.5% coverage at so-called 95% nominal level in order to be pretty certain of winning the bonus. And so that represents a quantitative way of seeing how much wider the intervals should be in order to be well calibrated. And I'll have more to say about that next week. So I'll talk about this thing that here is called Bayesian qualitative-quantitative inference next time, and I have a better name for it since I wrote this slide, namely distribution-free, well-calibrated Bayesian inference. Then we've talked about Bayesian nonparametric modeling, and I showed you on page 37, I showed you the answers, the actual data values, and the results in descriptive terms. And page 38, equation 6 gives us that familiar random effects Poisson regression model, which is the same as one of those, the PREP model we called it in that previous paper. Then we can talk about the thing we've agreed is a good thing to do. You relax the assumption of normality on the errors in this model, and that gives you that model I showed you before. And we have code that we could share with people that shows how to fit that model in fair generality. And also there's code at the CRAN website that should be able to fit this model as well. I'm going to do my best to bring that code to you next time. So you can think about Bayesian model averaging with a finite set of models, I'm on page 40 now, as like a crude approximation to what Bayesian nonparametric modeling is trying to do, namely averaging over your uncertainty in model space to provide an honest representation of your overall uncertainty that tries hard not to condition on things you don't know are true. So my sense of what's going on is that BMA was a good technology for the decade of the 1990s because it was the best technology people had routinely available to them. And it's still used to some extent in the 2000s, but I think particularly with small and medium-sized data sets, people are finding it possible to do Bayesian nonparametric modeling, which may well turn out to be a more satisfying generalization of the thing that Bayesian model averaging is trying to do. Now, I think I've hinted a little bit at this. I'm now on page 41. I think I've hinted a little bit at this calibration cross-validation idea before, but I'd like to take what time remains today to tell you the idea in a bit of careful detail, and then next time we'll actually see it work on some data sets. So one way to cope with model uncertainty is to pretend it's not there. It's sort of the ostrich approach where you stick your head in the sand and don't look around to see if something might be getting ready to run you over, for example. That was the M-star approach. We used the entire data set to suggest what models to consider, and then we condition on that same model that we got by that search and apply it again to the same data set. From the point of view of cross-validation, and we have talked briefly about cross-validation several times in the past, the usual thing is to partition the data into two non-overlapping and exhaustive subsets and fiddle around in one and see how well your models validate in the other one, right? From that point of view, we could call that two-way cross-validation. From that point of view, the M-star approach could be called one-way cross-validation. In other words, we don't attempt to have a validation set at all. We try to validate on the same data set we modeled on. And so one-way cross-validation is definitely bad. It more or less corresponds to Taylor series with only the constant term, so to speak. You're only taking the very first term in the Taylor series. Two-way cross-validation, here it's called two-fold cross-validation, but that's not a good name because some people talk about k-fold cross-validation, and they mean something quite different in terms of breaking the data set up into k chunks of one kth worth of the data, so to speak, and then you hold out one chunk and use the rest of the data to predict that chunk. 10 chunks each of 1/10 of the data, for example. So that word fold has already been used. So I wish on slide 41 it had said two-way cross-validation and one-way cross-validation above that. So under two-way cross-validation, you partition the data into modeling and validation subsets. Let's call them M and V. Then you use M to explore a variety of models until you found a good one. Let's call it M star. And then you see how well M star validates in V. And as I mentioned before, a useful Bayesian way to do this is to use the data in M to construct posterior predictive distributions for all the data values in V and see how they compare with each other. And you can do that informally, or you can do it formally using this tool log scores that I'll be talking about later. Clearly, two-way cross-validation is a lot better. It's something like bringing in the linear term in addition to the constant term in Taylor series expansion. It's got to be a lot better. But it has a dilemma of its own. Suppose you fiddle around in the modeling data to your heart's content, and you look at 17 different models, and eventually you pick your favorite one. Or in the spirit of Bayesian model averaging, you come away from the modeling part of the data with 3 models that look good that all should be Bayesian model averaged, for example. And anyway, you either use the single model that you like the best from the modeling part, or else you use the ensemble that you like best in model averaging, and now you try to validate it in the validation data. If it validates fine, then you're great, because you have answers to your questions, and you also have a way of saying to people how good the answers are. But what if it doesn't validate? And I must say, in the work I do with the Kaiser people, the people at Kaiser Permanente, we are all the time, despite our best efforts as analysts, coming up with situations where even with quite a lot of data, our models and the modeling part don't validate that well in the validation part. Even while trying to protect really hard against overfitting and all the, we're knowledgeable people and we've been doing this a long time, and we still find that our models don't always validate well in the validation subset. Well, now what are you going to do? You want to go back and remodel and then revalidate and keep remodeling and revalidating until finally you get something in the M part that actually does validate well in the V part. But now you've painted yourself into a corner because you had to use a highly iterative process that went back and forth between M and V to get something finally that worked, and you have no data left over to see how well that iterative process works on new data that hasn't been used in the iterative process itself. So if life is like a Taylor series, which in some sense it is, and we've already gotten out to the constant and the linear terms, why not do better than that by going out one more term? And so calibration cross-validation could also be called three-way cross-validation. And for a while, Milovan, I introduced the idea to Milovan, and he and I referred to it as 3CV, but I prefer the name CCV because it brings in explicitly the idea that the reason for the third component is to see how well calibrated you are. So now I suggest that we partition our data sets into 3 non-overlapping and exhaustive subsets: modeling, validation, and calibration, M, V, and C. And then we use, in step B of this algorithm, we use M to explore a variety of models until you've found one or more plausible candidates in an ensemble or set of models, script M, and there might be lowercase m of them, M1 to M lowercase m. And little m might be 1, but it might well be more than 1. Then step C, see how well the models in the ensemble script M validate in V. If none of them do, iterate B and C until you do get good validation. or if some of them do and some don't, then you can combine what you learned from the ones that didn't validate well to go back and improve the ones that apparently did. You're allowed now under CCV to do all the iterating back and forth between the steps B and C that you may like to do. And now finally, when you're done, you take the data sets, the data in the modeling part and the data in the validation part, and you move them together into one big data set, and you fit either the best model in your ensemble or use Bayesian model averaging on that unified data set, modeling plus validation. And now you're prepared to report two things. Roman numeral 1 down there at the bottom, page 42, inferential conclusions based on this fit, and also Roman numeral 2, the quality of predictive calibration of your model or model ensemble on the data in the calibration subset, which was not used in the fitting process. And my goal in using this method is twofold. I want both a good answer to the main scientific question, and also I want an indication of how well calibrated the modeling process is that led to that good answer. And moreover, I want a good answer in item 1 at the top of page 43. I want a good answer to the main question that has paid a reasonable price for my model uncertainty. And the way that price will play out is the following. If you did the M-star approach and looked around for a model on your whole data set and then fit that model to the whole data set again, if the whole data set has little n observations, then you'd be basing your iterative conclusions on all little n observations. Let's say little n is 1,000, and you use the M-star approach, which is something which is similar to one-way cross-validation. Then you would model on all 1,000 observations, and you would also validate on all 1,000 observations, and then you would also give answers to everybody on all 1,000 observations. And so your inferential intervals would be relatively narrow because you used all 1,000 of the data points in your inferential answers. What about in calibration cross-validation? I'm only allowing us to use not the whole data set, M plus V plus C. I'm only allowing us to use M plus V to base our inferential conclusions on. And if, for instance, you use an approach like half the data in M, a quarter of the data in V, and a quarter of the data in C, which is a good rough rule of thumb to use in this work, for instance, then you're actually only getting to use 3/4 of the data in the M plus V part of things. And you left out the other quarter of the data strictly for validation purposes. Now, if I use all 1,000 of the data points to draw my inferential conclusions, and you only use a random subsample of 750 of them, who's going to get wider uncertainty bands? Me or you? I use all 1,000 data points. You use only 750. Who's going to get wider uncertainty bands? You are, right? But that's appropriate because you are doing a better job of paying the correct price for your model uncertainty than I was. I was pretending I didn't have any model uncertainty by rooting around in the data set for a model and then pretending I knew it all along. So step 1 there says, item 1 says, I want a good answer to the inferential or the main scientific questions at issue, and a good answer that has paid a reasonable price for model uncertainty, because my inferential answer is going to be based only on M plus V, and that makes my uncertainty bands wider. Now an implementation question arises. How much data should you put in each? I just suggested as a rough rule of thumb, a half, a quarter. But of course, we can use Bayesian decision theory to answer this. The more important calibration is to me, the more data I would put in C, but only up to a point, of course, because if I put a tremendous amount of the data in C, then I'm not going to get a very accurate answer to the question I started with to begin with. And so the way I'm doing it right now with one of my students is, first we answer the question, how much data should there be in C by itself? And then having answered that question, we set that data aside and ask, of the data that's left, how much should be in M and how much should be in V? And that provides us a way to get all 3 of those fractions, adding and having them add up to 1. And another general purpose fraction you might want to consider is a third, a third, a third. But actually, I think a half, a quarter reflects my personal desires to have a bit more data in the modeling part to be able to really explore models as well as I can and still have information for calibration purposes. Machine learning people have been talking about something like this for a while now. Hastie and Tibshirani and Friedman, that nice book they published a few years ago, they call this approach train validation test rather than model validation calibration. But I have 2 improvements upon their way of looking at the world. One is that I know how to decide how much data to put in each of those subsets using decision theory. And the other one is that they claim that you can only use this approach on large data sets, but actually, if you think about when you need it the most on small data sets. And so what we probably ought to be doing is the following. With a small data set, I can make a single random partition to M, B, and C and do the whole exercise. And then I can go back and make another M, B, and C partition and do the whole exercise again. And I can average my findings across them as a way of seeing what's actually going on. You can use Bayesian model averaging across those repetitions. The one trick, though, in order to get the most information out of the replication process is you have to try to pretend when you're looking at the data on random partition 2 that you didn't see the things you saw in random partition 1. In other words, you have to take each one de novo and try to pretend you didn't see what came before. My wife and I play a kind of bridge where there are only 2 of us, and those of you who play bridge know that you usually need 4 people. And there's even a 3-person version of the game, but it's a terrible game, really. So how do we play bridge with 2 people? Well, bridge is a competitive game where we have two pairs playing against each other in a layout that can be thought of as north-south for one pair and east-west on the points of a compass for the other. So what my wife and I do is that each of us takes, in my case, I might take the south hand and the west hand, and I look at them both, and I bid them both. And then she takes the north and the east hands, and she bids them both. And we continue the bidding until the bidding is done. But here's the trick. You have to be honest about this. You have to make your bids pretending that you didn't see what was in the other hand. And actually, with some practice, you can get good at this. So that's why I'm bringing it up. With some practice, you can get good at ignoring what you learned from the other partitions and working only with what you see in these partitions. Or you have someone else do it, in which case you're back to having 4. Or you have someone else do the other partitions. That's a good idea. So we can do human parallel processing on this. That's a very good idea. When we have a small data set, we can do human parallel processing with different modelers, and then we bring our answers together at the end. That's a terrific idea. That's right. Okay, so that's calibration cross-validation, and I will be showing you how to do that on several interesting data sets next time. And now that we have agreed that there is a valid Bayesian way to pay a price for, in fact, the right price, not just a price, but the right price for hunting around in the data for good models, we're now ready to think about a kind of general purpose modeling algorithm that we could teach to a robot. And here's how it goes. It's in 5 steps. A, start at a model M0. And that gives rise to the implementation question, how do you choose where to start? So that's everywhere you see a question mark in this algorithm, we ourselves have an implementation issue to solve, and there are 4 of them. So suppose we could answer the how choose question somehow, and we figured out a good place to start. Now, the current model is now M0, because we're about to have an iterative algorithm where we'll have potentially different current models later on. So I create a model called mCurrent, and I set it to M0, and I create, from what was previously an empty set, I create a current model ensemble, or list of models that I want to retain, called scriptm subcurrent, by adding model 0 to it. Now, step B, look at your current model. If it's good enough to stop looking for other models, then stop. So the algorithm returns your current model ensemble, and then you have another choice to make at the end. If the ensemble contains more than one model, then you can decide to do Bayesian model averaging if you want to. Or you'll see as a result of this algorithm that the models are going to be ordered in mCurrent from worst to best. And so you could just choose to pick the best one, the right-hand most recent one in mCurrent if you want. So there's our stopping criterion in step B. But how do we decide whether the current model is good enough to stop? That's another implementation issue we'll need to face. Then under step C, now we've decided not to stop because we didn't stop in step B, so we have to keep going. So under step C, generate a new candidate model. I'll call it mnew. And again, that gives rise to an implementation question. How do we choose the new candidate model? And then set the mCurrent the script M current, the current ensemble, equal to the old one with the new one added to it. So we just take the union of the old one and the new. Now in step D, we need a way of deciding whether the one we just added is better than the current one. And if it is, if M new is better than M current, then let's set M current equal to M new. And again, that gives rise to the fourth implementation question. How do you decide when M new is better than M current? And if you've gotten this far in the algorithm, just go back to step B and keep going. So this is bad programming. I have a go-to step in it. For those who like to do structured programming, this has a go-to in it, but I hope you can forgive me on that. And there you go. Now that's actually an algorithm that we could teach a robot to do if we could answer those four implementation questions. But let's talk about the first one. How do you tell a robot where to begin? In a regression setting, for example, you could say to the robot, well, start with a model that doesn't have any predictors in it at all. That's a good starting point. It's a rubbish model, as we'll see later on, but it's a good place to start. In a one-sample model, and by the way, when you're working in regression, of course, the choice of regressors, the choice of predictor variables is very much not the only thing you're uncertain about. What are some of the other things we do in building regression models? We consider transforming the y variable. We consider transforming the continuous x variables. We consider bringing in interaction terms. We consider bringing in quadratic and cubic terms. We do lots of things like that. And then when we're done, we have to think about what we want to use for the so-called error distribution. Is it a Gaussian? Is it something else? Is there that thing called heteroscedasticity where some rows in the data set have bigger amounts of variability in them than others do? What should we do? So there's lots of choices to make. If we can figure out how to teach the robot how to start, then we need to give it a rule for deciding when things are good enough to stop. And I'll talk about that in a minute. There's a similar choice to be made in step D. I have two models I want to compare. How do I know when one is better than another? So how do I decide whether one's better than another? That is, of all these four questions, that's the one that's been given most attention methodologically in the Bayesian story. We now have a bunch of different methods for comparing one model with another, and I'll be giving you all those details next time. Of all four of those things, I don't think how choose in step A is that hard. For human analysts, that choice, of course, is not hard. And you can always tell the robot to start at some null model of some kind. There's probably some off-the-shelf model that it could start with, based upon the structure of the data, for example. But the hardest question of all four of those is the one in C. I'm at a model right now, and I've decided that it's not good enough to stop searching, and I want to keep going by some means, and I haven't told you yet how to do that. How do I decide where to move? This is the one that I referred to as NP-hard. This is too open-ended for it to be straightforward to teach a robot how to do. We human analysts have developed experience in it over time. And so we have some rules that we use. And I suppose you could make a robot smarter and smarter over time by teaching it more and more of those rules. But have any of you ever tried to construct rules-based systems in which you give the thing more and more if-then statements? And what you find at the end is there's still lots of situations where it doesn't know what the hell to do because it doesn't satisfy any of the ifs that you had. So that's a way to progressively make the robot smarter with better and better systems of if-thens or sets of if-thens, but it's hard to get all the way to where you want to go. So I tell the robot I'm going to look at a one-sample problem. I have y1 through yn, and my basic model for them is De Finetti's model that the yi's, if I knew what f is, they're conditionally IID from f, but I don't know what f is. Model 0 for the robot could be, okay, yi given mu and sigma squared, IID normal mu sigma squared. And then the rest of the model, from a Bayesian point of view, it has to put a prior on mu and sigma squared. And it might choose a diffuse prior if you told it that problem context said you didn't know much about mu and sigma squared external to the data. Now, we human analysts, because we're allowed to now because we have CCV, we're allowed to poke around in the modeling part of the data. We make a histogram of the data values, and the histogram looks like this. And so we human analysts say, oh, model 0 was a mixture of one normal distribution, and the data shows clear bimodality. So I'm probably going to need, if I'm going to go in that way, I'm going to probably need a mixture of at least two normals. And I don't know how much experience you have with mixtures of normal distributions, but something that looks like this could actually be better represented by a mixture of three normals than of two. Even though it looks like it only has two distinct humps in it, you might need one in the middle to fill in the difference between them, for example, the distance between them. So human analysts would say, gee, that sure doesn't look unimodal to me, so I better improve model 0 by working with a model that perhaps is a mixture of Gaussians. And I might start with pretending that there were two mixture components and move up to three if I had to, for example. So now there's a rule-based method we could give to the robot. We could say, if you're in one sample settings, do some kind of check for multimodality. And that would be and you could ask it to make a grid of the density heights that it got from the density function and look and see if the densities were monotonic increasing up to a maximum and then monotonic decreasing. Then the then part of the rule would be fit a mixture of Gaussians where the number of mixture components at first is 2 and then try 3. And then actually now you're going to start having to answer the question, is it better to have 3 components than 2? So now we're down there in item D. But so you can see how a human would suggest a new candidate model by various sorts of diagnostics, some are graphical in nature, some numerical in nature. I suppose if you went around and shadowed, if you were sharp and you went around and shadowed a very sharp data analyst over a long period of time, you could harvest enough of these if-then rules by watching what this person did to create a pretty smart robot. At least the robot would know to do all the stuff that that person did of all the things you ever saw that person do. And that person might have other tricks up his or her sleeve that you didn't see yet, but at least you would have gotten all the ones that you saw. Has anybody ever done this? No. I think I told you about my friend John Adams from RAND, who did some work that I mentioned briefly in that model uncertainty paper we looked at last time. He created a kind of expert system. It was a kind of robot that explored all the different things that people tend to do in regression settings. Transform the Y, transform the X. I just gave you that laundry list before. And you remember what he did? He gave that robot hundreds and hundreds of data sets in which there was no signal at all. Everything was completely noise. And he asked it to tell him at the end of that how often it found interesting patterns, even when he knew, and the robot didn't, that there was nothing interesting going on at all. And he thereby showed that people who use the standard prescriptions for regression model fitting in standard textbooks without cross-validation are probably hideously overfitting their data because his robot was all the time finding signal when it wasn't really there. So that's the closest I've ever seen. He almost built an expert system for regression by those means. But he just left that. It was his PhD dissertation. He wrote an article about it and then dropped it. The code probably isn't even available anymore. I don't know where it is. He doesn't do it anymore. So no one knows how to automate this. But humans, if you yourself were to try to use this flow chart, and I will show you examples of it next time because I've used it myself, you can use your own human ingenuity to have a decent way of moving from where you are to the next place. I have figured out a picture that goes some distance toward what we want, except it only goes far enough to be tantalizing and then leaves you in the lurch. What we want to make an automated way to figure out where to go next is we want something like this. We want a measure of the distance between models on the horizontal scale, and we want the quality of the models on the vertical scale in a direction where high quality is up here. High is better, big is better on this scale, and low down here is worse. And 0 distance corresponds to exactly the same model. So, for instance, let's talk about distance between model 0 and model 1. And on this quality measure, model 0 lands right there. It has a distance from itself of 0, and it has a particular level of quality. That's model 0. It turns out you can create this distance measure by using something called a symmetrized version of Kullback-Leibler divergence. And I'll talk about what that is next time as well. It's a symmetrized Kullback-Leibler divergence. So there is a method for measuring how far models are apart, and I can quantify that and go like this. And I'm going to use as my measure of quality of scores, I'm going to use those full sample log scores I told you about. So that's going to be my vertical. So I know how to make this picture operational. For example, suppose model 0 for you was that the data were yi given, let's see. Suppose model 0 was yi's are IID normal 0, 1. That's not likely to be a very good model for any old data set that you toss at it, right? Because if the data values are all above 50, then this is a pretty bad model. But it has some measure of predictive accuracy with the log score thing, and I'm going to call that value right there. Right away, if things really were Gaussian, how could we improve this model? This model pretends we know somehow that the mean of the data engineering process is 0 and the standard deviation is 1. So right away, if we left the standard deviation at 1 and just let the mean be unknown and tried to learn it from the data, that's got to be better, right? So let's try as model 1, yi given mu are now IID normal mu, comma 1, and make mu diffuse, for instance. So there's our Bayesian, little teeny Bayesian hierarchical model. Well, you can compute the distance between model 1 as a function of mu and model 0. And if the actual data generating mu is right here, what you'll find when you start tracing these things out is a very pleasing thing happens. The log scores improve until they get to the data generating value, and then they get worse again. So look, it's starting to look like we might be able to teach the robot something, because if we could only get it on this curve, then it can automatically find the highest point on the curve. So I was asking the question, how do we choose a new model? And the answer is, within all of the different models that have different mu's, you robot get to choose lots of different mu's until you get up to the data generating one, and then it falls off from there. But suppose we've now found the best model within this model class, where mu corresponds to the posterior mean or something like that, for instance. How do you launch yourself from this curve to a new curve that's even higher than this one? Well, we humans know what the answer would be. You go, all right, well, since I gained some traction by allowing the 0 to be whatever it was and learn it from the data, now let's free up the 1 and make it go from 1 to unknown and learn about them both with diffuse prior. And now what you discover is that for some values of sigma, these are actually worse than mu equals 1. But for other values of sigma, you get even better values than what we had before. So again, if I could tell the robot to jump from this curve to this one, I could then automate its solution of finding the best point there. But again, the problem is always, how do I get from one of these curves to the next one? I have to bring in an ingenuity leap that the robot doesn't know how to do. Once I get it on one of these curves, it can do the thing, it can do the optimization thing itself and find the best one. But this is a hard problem. I've never met anyone who knows systematically how to solve this problem in a way that could be programmed into a robot. But that's okay, because even though we don't have this robot to help us tonight or tomorrow night, we still have time tomorrow ourselves or Monday or Tuesday or whatever to implement this 5-step algorithm ourselves. So now I turn to, having said that question C is too hard to be able to say anything about very generally, and having said that the question in A is not that hard for humans, let's now turn for the last few minutes here to answering questions B and D from a human point of view. Questions B and D look like the following very basic questions. Question 1, is Model 1 better than Model 2? Question 2, is Model 1 good enough to stop looking? Those do sound quite basic. But the more I thought about this, the more I realized that they're not actually at the core yet. They're one step above the core. Because if you asked me, you came up and said, I've got 2 models here, and I'm wondering if you can help me answer the question, is one of them better than the other one? I would really have to answer your question with another question, namely, is Model 1 better than Model 2 for what purpose? What are you going to do with these models? Can you imagine a situation where in situation 1, you are only interested in rather gross characteristics of the stochastic story you're watching? For answering sharp, blunt, gross sort of questions, a particular model might be plenty good enough. So the same thing applies to question 2. Is Model 1 good enough to stop looking? If the purpose of your modeling is to answer a pretty simple, blunt instrument kind of question, then a rather simple model might be good enough to stop. But if you're in the same setting, your purpose is to answer a very careful, delicate question, then that previous model, which a minute ago was good enough to stop because you had a rather blunt instrument sort of question you were asking, is no longer way no longer good enough to stop. And so both of these questions actually have another question hidden underneath them. Is Model 1 better than Model 2 for what purpose? Is Model 1 good enough for what purpose? And once you specify that purpose, you are, whether you meant to or not, you are in the world of decision theory again, because you're having to place values on which models are better than which other ones according to what dimensions. And so that's utility, actually. Other people have noticed this around the same time I did or before, and it leads me to articulate a principle here that I'm going to call, for the rest of the short course, the modeling as decision principle. And what it says here, I'm on page 45 of part 5 of the notes, it says, making clear the purpose to which the modeling will be put transforms model specification into a decision problem, which should ideally be solved by maximizing expected utility with the utility function that's tailored to the specific problem under study. And unfortunately, when we write down principles, we sometimes find that those principles are hard to attain. We know that they ought to be what we're striving for, but we find it difficult to actually attain those standards. I can think of several principles regarding my own personal conduct that are definitely principles that I should like to live by, but I find quite difficult to attain, and I bet you can too. Principles have this way of being admirable and hard to achieve at the same time, often. I have written a paper with my Greek student Fuskakis, and I should post that to the course page here, in which we showed how to build a utility function that actually quantified which models were better than which other models for the actual purpose of the modeling. And then we did a search in model space and maximized expected utility. And it was a cool thing to do. It was a hard piece of work, but it works. So it can be done. There are existence proofs from papers like that one. I'm not able to tell you very many other papers that actually do it. So I think you'd probably agree with me in the second part of that sentence in that paragraph, there is a powerful desire for generic model comparison methods whose utility structure may provide a decent approximation to what the problem-specific utility elicitation would have been if you'd gone through the trouble of doing it. In other words, wouldn't we like to have general tools for answering these questions, even though I just got done convincing you, I hope, that these questions really are quite specific to the problem you're working on? Is this model good enough to raise the eBay bottom line by blah, blah %? Is this model good enough to get Google an extra 50,000 clicks on those sponsored ads? There's a purpose behind this stuff. And to do it right, we have to say what the purpose is, and then you will find that your way of deciding whether one model is better than another is driven by the purpose. But that's hard work. And so people look around for generic model comparison methods that either have utility bases or appear to have utility bases, or else maybe they have utility bases, but the utility function isn't very good. And that's what we're going to get started with next time. Two of these methods that I do need to tell you about are Bayes factors on the one hand and log scores on the other. And I've been telling you a bit about log scores around the edges for a while now, but I'm going to do a more systematic job of it next time. Bayes factors are a sore spot in the Bayesian history for decades now, because they look like the right thing to do from a certain point of view theoretically, and yet they turn out to be extraordinarily difficult to implement in a way that creates a kind of stability, a kind of robustness. That's the sort of thing that you would want to have a good scientific method. So there's a special case of Bayes factors that corresponds to that BIC idea we used this morning in that software BMA. And so my main advice to you is going to be, if you think Bayes factors are okay, you're probably going to want to use BIC as a general all-purpose method for computing an approximate Bayes factor when BIC is available, because it turns out it's not always available. And then log scores are going to be competitors to Bayes factors, and I'm going to have some things to say of a pro and a con nature about both of them. So that gets us pretty much to where we have run out of time for this week. I have not provided you with any more problems to work on. I'm behind on that, but I hope I've given you substantial food for thought. And there's a bunch of stuff to read here that I didn't get a chance to cover today to read in some detail if you have extra time for reading. So it would be terrific if people were able to do some reading outside the class and come armed with sharp questions about what they read, because I love hearing sharp questions about my work, because it is a good way to try to improve my work when people ask sharp questions that force it to be improved. So once again, thank you for coming today, and we'll meet again here a week from today in this same room.